Hello everyone, welcome back to JM Lectures. JM stands for Just Mary, that would be me. Today we're going to be continuing the grade 12 physics Matric questions. We are on unit 7, Electromagnetic, Induction, and AC circuits. So let's move on to the question. Question number 27. A magnetic field of strength 5 times 10 to the power of minus 5 Tesla passes through an area of 20 centimeters squared that is at an angle of 60 degrees to the magnetic field. What is the magnetic flux? So this question has to do with magnetic flux. Magnetic flux, represented by the Greek symbol phi, is simply explained as the measure of the effect of a magnetic field on a certain area. So we can see in this question, what we have is some magnetic field. Let's say this magnetic field can be represented like so. Now this magnetic field with a magnetic field strength of B is experienced by some surface. Let's say we have a surface like so with a certain area A. And this surface is at an angle of theta. So the formula to calculate magnetic flux is given by phi is equal to B times A times the cosine of theta. So this representation is a very excellent way to describe the effect of a magnetic field on a certain area. So magnetic flux is a very important quantity whenever you're trying to discern the effect of a magnetic field on different bodies. So let's move back to the question. We see that we are given the magnetic field strength B, which is equal to 5 times 10 to the power of minus 5 Tesla. We're also given the area of the surface that this magnetic field acts on. And this area is given as 20 centimeters squared. Now we should probably change this into meters squared. We can simply do that by saying 20 times 10 to the power of minus 2 meters squared. This will give us 20 times 10 to the power of minus 4 meters squared. Lastly, we have the angle that the surface is relative to the magnetic field, and this angle is given as 60 degrees. Now, very simply, we can move on to the solution. We use the above formula that magnetic flux is equal to the scalar product of the magnetic field strength and the area multiplied by the cosine of the angle between the two. Filling in these quantities, we have magnetic field strength as 5 times 10 to the power of minus 5 Tesla. We have the area. Let's move this just a bit so we can see a bit clearer. We have the area as 20 times 10 to the power of minus 4 meters squared, and we have the angle as the cosine of 60 degrees. Now let's see if we can simplify anything here. We have the cosine of 60, we know is 0.5, so we keep that in mind. We also have 5 times 20, that'll be 100. We can multiply that 100 by 0.5 to get 50, right? So we have that the magnetic flux is 50 times, let's see these, the 10 to the power of minus 5 and 10 to the power of minus 4. You can put that together as 10 to the power of minus 9, which is simply minus 5 minus 4. And what about the unit we have? Well, we have the unit of Tesla and meter squared. So Tesla times meter squared is actually this new unit known as Weber, represented by WB. We can simplify this a bit more. We can get rid of this 0 and turn this into a minus 8. And we would finally have that the magnetic flux is equal to 5 times 10 to the power of minus 8 Weber. That would be our final answer. And if we take a look at our choices, we can see that that would be choice C, 5 times 10 to the power of minus 8 Weber. So it's a pretty straightforward question. It's a very important quantity. That's what you really have to take away from this. Magnetic flux is an important quantity, and this simple formula can be used in order to calculate it. And that's it. Now we're moving on to the next question of electromagnetic induction and AC circuits. Question number 28 states that, which of the following is correct about the characteristics of current and voltage in AC circuits? The choices are A, if the current is in phase with the voltage, the circuit is inductive. B, if the current leads the voltage, its capacitive reactance is greater than inductive reactance. C, if the current leads the voltage, it is inductive. And choice D, if the current lags the voltage, the circuit is capacitive. So There's a bunch of different, slightly confusing choices in this question, but let's first go to the general concept of what it means when we say an AC circuit. So first, in order to understand AC, we actually have to know what DC is. So these two concepts go hand in hand, a DC and AC circuit. DC is actually a way to describe direct current, and AC is alternating current. All this simply means is if you try to analyze the current over a certain amount of time, in a DC circuit, the current does not change. It doesn't fluctuate. It stays at a constant value, whatever that is. In the case of an AC circuit, however, the current and the voltage actually both fluctuate or alternate, as the name says, an alternating current or an alternating voltage. So this alternation is usually visualized as a sinusoidal wave, meaning it increases, it decreases, it increases and decreases again. So this alternating current is what we see in AC circuits, an alternating current, as well as an alternating voltage. So this is the basic difference between a DC and an AC circuit. So you might wonder in reality, what would be the applications of these two different currents? Well, the DC current is what we use for most of our electronic devices. We need a direct supply of current in order for these to work. But from power stations, we usually have an AC current that is being supplied. So this AC current can travel long distances, can be manipulated by transformers to step up or step down the voltage, and then finally when it reaches where we need it to be used, it'll be changed into a DC current. So I'll have another video with giving greater detail for this concept, but for now, this is enough of an understanding that we need. So now we're moving on to the question where it describes three basic types of AC circuits. We have a resistive, a capacitive, and an inductive circuit. Yes, there are other circuits where you have combinations of these, but understanding these three basic ones makes any other combination much more simpler. So let's start with a resistive circuit. A resistive circuit, like the name says, is simply a circuit that contains a resistor and some sort of power supply or the voltage source. So this voltage source creates a current that will flow through the resistor. Similarly, we have a capacitive circuit, and a capacitive circuit, let's say you have a capacitor represented like so, and this capacitor is also connected to a voltage supply or some cell like so. Be sure to be careful of the difference between a capacitor and a cell. You see how in the capacitor, the two legs are equal, while in a cell, you see that one is longer and one is shorter. So similarly, we also have a current flowing through this circuit. Lastly, we have an inductor. This capacitor, let's say, is C. Lastly, we have an inductor. This inductor can be represented like so. And again, this will be connected to some cell. This cell has a voltage and it'll supply a current to the inductor. Now, we have to be able to analyze these three circuits individually because they have different characteristics when they are reacting to a voltage. If you go to the first situation, a resistor, the simple formula that relates the voltage, the current, and the resistor is the voltage is equal to the current multiplied by the resistor. This is known as Ohm's law. For a capacitive circuit, the current is equal to the capacitance multiplied by the change in voltage over time. And for an inductor, the voltage is equal to the inductance multiplied by the change in current over time. So these formulas are slightly different. They actually have a big impact when we're talking about AC circuits or alternating currents. If we look at resistive circuits, in resistive circuits, you will have that the voltage and the current are what we say are in phase, meaning that the peaks of the voltage and the currents and the troughs of the voltage and the current are at the same point. If we wanted to represent this graphically, we can see that. Let's keep in mind, for the rest of the video, we say that voltage is blue and current is green, okay? So if the voltage is something like this, because remember, we're still on AC circuits, well, the current will be something like this. You see that they are more or less the same shape. And this similar shape is how you represent the voltage and the current being in phase for resistive circuits. Another way to represent this is with a phasor diagram. So a phasor diagram looks a bit like this. And if we say our voltage is at the 0 degree angle, like so, let's say if our voltage is like this, well, our current will also be at that 0 degree angle because they are in phase with each other. Since they are in phase with each other, the voltage and the current can be represented in a phasor diagram like so. Moving on to a capacitive circuit. Well, in a capacitive circuit, current and voltage acts a bit different. In a capacitive circuit, the current actually leads the voltage. So again, we have our diagram like so, and if our voltage is still in the blue, represented like this, well, if our voltage looks like this, our current leads our voltage. It leads it by exactly an angle of 90 degrees, or pi over 2. So you represent this, the current leading the voltage, like so. So the current leads the voltage like so. So how we represent this with a phasor diagram, again, if we have our phasor diagram looking like this, well, let's say our voltage is at the 0-degree angle. And again, to say that our current leads the voltage, we represent it like so. So our current in green and our voltage in blue is given like this. So you say the current leads the voltage by an angle. This angle is pi over 2, where pi over 2 is 90 degrees. So again, in a capacitive circuit, the current leads the voltage. What about an inductive circuit? Well, in an inductive circuit, again, let us represent the waves like so. If the voltage is given like this, then the current in this case lags behind the voltage. So the current lags behind the voltage, and this can be represented like so. The current lags behind the voltage like so. How you can represent this in a phasor diagram can simply be, again, if our voltage is at this 0-degree angle like so, our voltage is the one in blue and it's at the 0-degree angle, our current will lag behind the voltage. So you usually represent this like so. Our current lags behind the voltage. Again, this is at an angle of pi over 2, or at an angle of 90 degrees. So the reason behind these differences in the current and the voltage of a resistive, an inductive, and a capacitive circuit, well, these differences lie in the characteristics or the properties of resistors, capacitors, and inductors. I'll probably make another video going in further detail of why they react in this way. Just to be clear, just to make this a bit clearer, let me quickly differentiate the colors between the two so we have this all represented clearly. All right, now we can move back to the choices. Let's see the first choice. If the current is in phase with the voltage, the circuit is inductive. Well, no, we saw that if the current and the voltage are in phase, that is in fact a resistive circuit. Don't forget, in a resistive circuit, the current and voltage are in phase, so that can't be the correct answer. If we look at choice B, if the current leads the voltage, again, if the current leads the voltage, what case is that? That's a capacitive circuit if a current leads the voltage. It says that the capacitive reactance is greater than the inductive reactance. Reactance is just a fancy way of describing the resistance of capacitors and inductors. You can't really use the term resistance, so you have a new term called reactance. So to say that a capacitive reactance is greater than the inductive reactance, it's simply to say that the circuit is more like a capacitive circuit than an inductive circuit, which is correct, because the capacitive circuit is the case where the current leads the voltage. So let's take that as our correct answer, but let's first move on to the other choices. Choice C states that if the current leads the voltage, it is inductive. No, if the current leads the voltage, it is capacitive, so that can't be the answer. Choice D states that if the current lags the voltage, the circuit is capacitive. No, if the current lags the voltage, the circuit is in fact inductive. So we were correct. Our correct choice is in fact choice B. To actually help you out in this question, you can use a bit of logic to get rid of choice C and D without even understanding the concepts. Because if you see the two, C and D are exactly opposite, right? They're stating two opposite facts. And I've done this kind of question before. With logic, they're either both the choices are correct or both the choices are incorrect. Since this is a multiple choice question, both of the choices cannot be correct. Only one correct answer is available. So you can just conclude that both the choices are incorrect. This is sometimes, if you're ever having trouble picking the choices, this is one way to figure it out. But still, for this question, the correct answer is choice B, and that's it.